All right, well, good morning, and we'll take a look at today's lecture. So we introduced some maximum likelihood ideas, and we showed that maximizing the likelihood, if in kind of a linear regression model or just any kind of model where you're trying to, if you assume the errors are normally distributed, that is equivalent to minimizing these sum of squared errors. Okay, so we showed that last in our last lecture. Let's just today I want to look at the variance, maximum likelihood of the variance, and so we'll revisit the likelihood function. So if we have kind of a linear model where the predicted values are, say, this value, W times X, so W transpose X of N, and we're assuming the true values are normally distributed around this, this mean. And we have some kind of variance sigma squared, then we'll take the PDFs, which is given by this, and then because all of the observations are assumed to be independent of each other, then the total likelihood of our entire data set will be the product of all of these different observations, the probability for all of these observations. Okay. And we said, you know what we want to do is we want to maximize the likelihood with respect to W hat, and we found that it is equivalent to minimizing the sum of squared errors, because if you take the log of the likelihood, then the log cancels out this exponential function. This stuff up here just ends up being a constant, and then as far as the stuff inside the exponential function, basically we have the sum of squared errors right here. It's preceded by a negative constant, and therefore if we're trying to maximize the total log likelihood, then we want to shrink the sum of squared errors to be as small as possible, so that this negative constant, after it's multiplied by this negative constant, the result is as small as possible. And so, solving for that, we get, our very familiar solution, X transpose X inverse times X transpose T. Okay, that's the solution we're familiar with. Okay, what we want to do now is we want to say, well, can we maximize the likelihood function with respect to the standard deviation or the variance? Okay, and so this is kind of our log likelihood function, and we're going to say we want to kind of maximize this with respect to our sigma here. Okay, and so what I'm going to do is I'm going to take our MLE estimate of W. All right, we're going to plug that W hat in, and we're going to kind of treat it as a fixed value. We saw that our estimate of W hat does not depend on sigma at all. It really just depends on X. Okay, and so we want to see, okay, can we plug that in and maximize this with respect to sigma? So what we'll do here is we'll just use calculus. We will take the derivative with respect to sigma. We will set that equal to 0, and we'll solve for sigma here. All right. So taking the derivative of this with respect to sigma, this is a constant, so that zeroes out. Negative n log sigma becomes n divided by sigma, negative n divided by sigma. And then over here, basically I have negative 1, I get negative 1/2 times sigma to the negative 2. And so that negative 2 cancels out with the negative 1/2, and I'll get sigma to the negative 3. Okay, and then as far as with respect to sigma, this entire summation is just a constant, whatever it is. Okay, as far as comparing it to sigma. So we set that derivative equal to 0, and we're going to solve for sigma. And so I'll add n over sigma to both sides, and then I will multiply the left and right side by sigma cubed, which gives me, and then divide both sides by n. So I'll get sigma squared over here. Dividing both sides, I get 1 over n. And then so kind of my estimate, the estimate of sigma squared that that minimizes the variance turns out to just be the mean squared error of our model. So this is going to be the value that gives me a derivative equal to 0, which will correspond to kind of our maximum. And so this is just our squared errors and 1 over n, so we just get the mean squared error of our model. Okay, and then I will plug that estimate of sigma squared hat back into our log likelihood. Okay, and so so I can do that. If I see a sigma here, I can plug in a sigma squared and just divide it by 2 out here. So I get this, and then I get negative, just kind of plugging in our sigma squared hat there. All right, and then just kind of simplifying a couple things here. All right, so if you think about, if we know that this thing, if we know sigma squared hat is, what do you call it? The sum of squared errors, or I'm sorry, the mean squared error, then this quantity over here becomes n times sigma squared hat, or sigma hat squared. Okay, so the sum of squares is n times our MSE, right? So sigma squared hat is our MSE, so this becomes that. And so so this will cancel out with this, and I am left with basically negative n over 2 log 2 pi minus n over 2 log sigma squared hat, or sigma hat squared, minus, and this just becomes negative n over 2. I can combine these things, and I get negative, well, I guess I can just factor out n over 2 out of everything, but here I get 1 plus log 2 pi minus n log sigma squared. And so this is the log likelihood, okay, of our entire, I guess our model here with our data. And what we see is that, so this is just a constant, okay, but our log likelihood does depend on our sigma squared value. And so if this gets bigger, okay, if sigma squared gets bigger, then our log likelihood, because there's a negative value in front of it, will shrink. Okay, so as our the variance of our data increases, then the overall log likelihood will shrink. Okay, and so what's the intuition behind that? Well, we can think of kind of sigma squared as kind of the error of our model. The error is basically just, you know, after you have your prediction line and you have scatter around it, the error is basically your leftover variation, that scatter. And so one way to kind of decrease the amount of errors to make a prediction function as complicated as possible, so that the remaining error is as small as possible. Okay, and but we also know increasing the complexity of the model, which can maximize the likelihood and reduce the error, but we also know that an overly complex model might not be the best. Okay, but basically, you know, this sigma squared is kind of your leftover variance, and if you want to shrink that, you can just kind of make your model as much, you know, as complicated as you need it to be. All right, let me give you your first view quiz answer, which is the letter A. A as an apple. A as an apple is our first view quiz answer. All right, so let me let me introduce a little bit of kind of this brief I don't know, brief introduction to this topic of Fisher information, okay? So okay, let me just back up a tiny bit and let's think about derivatives and second derivatives and all of that. So if you just have a univariate function, your first derivative, that basically tells you kind of the slope of the tangent line. It's kind of the rate of change, right? How quickly is the value changing as the function is kind of, as you're incrementing x. And so if you have a steep slope, then that means if you change x a little bit, then the value of the function changes a lot, right? Okay. The second derivative tells you about the rate of change on that slope, okay, which to us is a measure of its curvature. So if you have a large second derivative, it means your slope rapidly changes. It might go from a very steep positive slope to a very steep negative slope, okay? So it's kind of rounding out this, there's a sharp bend or sharp turn in the curve, you would have a high second derivative. If the slope changes very slowly and gradually, then your second derivative is going to be, very small, okay? Or we'll have a small absolute value. And so, so that's what the second derivative tells us. The sign of the second derivative tells us about the concavity, right? Is it concave up or concave down? Is it going from uphill to downhill, or is it going from downhill to uphill, or something like that? That's kind of what the second derivative tells us, right? And then if we know the value that the first derivative is equal to 0, meaning the tangent line is flat, and then the second derivative, if the second derivative is positive, okay, then then the function is concave up at that point, and x would correspond to a local minimum. If the second derivative is negative, okay, meaning it's going from positive to negative, then then the function is concave down at x, and it's going to be a local maximum. And if your second derivative is equal to 0, then we don't really know the concavity of the function at x. X could be an inflection point. You have these kind of saddle situations, things like that. So that could be the case as well. Okay. All right. So we want, if we generalize this to a multivariate function, okay, we have kind of similar or analogous concepts would be things like the gradient for the derivative, right? So we can generalize a lot of the kind of intuition behind the derivative to the gradient. And so now you have your function, the input is like multiple values coming in. The function still outputs just one value, okay? So if the input to the function is a vector from w1 through wn, then the gradient with respect to that vector w itself is a vector of all the partial derivatives. So it's going to be the partial derivative with respect to the first component of w and partial derivative with respect to the second component of w, so on and so forth. And this is, you can kind of think of the gradient as, a multivariate generalization of the derivative. And then if we want kind of the second derivative, all right, then we get the Hessian matrix, okay? So if you think of all of the, so if this is the gradient, we have this vector of length n of partial derivatives, then the kind of second derivative, all right, so if we just take all of those partial derivatives and we take what is the gradient of this partial derivative with respect to w, then we will get another vector of length n. And then I will say, what is the gradient of this partial derivative with respect to w, okay, then we'll get another vector of length n. And so we end up getting this n by n Hessian matrix. And so this is the second derivative with respect to w1, okay? Or I guess, you know, partial derivative of f with respect to w1 and w2, and so on and so forth, okay? So this is going to be a matrix of second derivatives. And you can think of it as just kind of taking each of these partial derivatives and saying what's the gradient with respect to w, and that's going to itself produce an entire vector of length n, and we're doing it for all of the n components in here, and so we end up getting this n by n matrix of partial derivatives, or a second order partial derivatives, and this is known as the Hessian matrix. I think you guys have seen this in what, 32a? B? 32? Something, right? Math 32. Okay. So yeah, so here it is. You know, take this first component, and then you just get this length n thing, and you have this, you know, that's your first column in the Hessian matrix. Yeah, it's been a while, so a little bit of review, right? Okay. So with a univariate function, you can kind of take the sign of the second derivative, and that will tell you if it's concave up or concave down, okay? And then if you have kind of a multivariate function, and we have this kind of matrix, right? Then you have this concept of definiteness, okay, of a matrix, right? And so you have, you know, things like positive definite and negative definite and positive semi-definite and all of this and that stuff, right? Okay, so if you have the gradient of the function is equal to 0, right? So you calculate the gradient of the function, and basically it's a vector of zeros. And then the Hessian matrix is positive definite, which means when you do kind of your eigenvalue calculations, the eigenvalues are all positive. Then this function is concave up at that point x, and x would correspond to a local minimum. If the Hessian matrix is negative definite, that means all the eigenvalues are less than 0. Then the function is, you know, kind of concave down, and it would correspond, you know, your value x would correspond to a local max. And then, you know, if your Hessian matrix has both positive and negative eigenvalues, then you've got a saddle point, and you know, I don't know. So it could be concave up in one direction and then concave down in the other direction. So you have something like that. If you have eigenvalues that are equal to 0, then we're not quite sure. We need more information. I think this covers the different situations and stuff, but that's kind of, again, a lot of times it's easy to think about functions in one dimension, at least in my brain. One-dimensional functions are easy to think about and reason about, and for me, a lot of these kind of higher dimensional concepts, I try to think of like, okay, what is the one-dimensional analog to kind of get my head wrapped around these things. Okay, so the Hessian matrix is equivalent to the Jacobian matrix of the gradient function. Oh yeah, all of these terms, right? Hessian matrix is usually symmetric, and so I would say, yeah, again, usually symmetric. So, but it might not be symmetric if you have second derivatives that aren't continuous or something like that. There's different theorems. Short's theorem, if the second derivatives are continuous, then the order of differentiation does not matter. So technically, over here I've got you know, partial with respect to W1 and the partial with respect to W2, and here is kind of the opposite order, partial with respect to W2, partial with respect to W1. Or am I reading this backwards? I don't know. But anyway, Schwarz's theorem says if everything is continuous, then these two things, the order in which you kind of do this partial derivative stuff, order of differentiation, doesn't matter, and this matrix will end up being symmetric. Okay? All right, hang in there. Okay. So the Hessian, it's useful to us because it can tell us about the curvature of the function. If you apply it to, say, the likelihood or the log likelihood of the function, we get an idea of the curvature of that function, and that in turn can tell us kind of how confident we can be in our parameter estimates. So, so this is kind of the next leap here, and so I'm going to kind of explain this in the univariate case, and then I'll just have to say, you know, just imagine the similar kind of idea happening in the multivariate case. Okay, all right. So so let's say, okay, here is, I have a pouch, and imagine I've got marbles in here. Some are red and some are blue, and we're trying to guess what proportion of the marbles in here are red. Okay, but we're playing a game, and I'm not going to let you actually look inside the pouch. And what we're going to do is I'm going to pull out a marble one at a time, and I'll show it to you. I'll put it back in. I'll shake it up. I'll pull out another marble. We'll put it back in. And so we'll keep track of the different colors we've seen. Okay, so let's say I draw 10 marbles with replacement. So far we see 4 red marbles. Okay, all right. And so we can say, okay, what is, if we're going to say the proportion of red is given by the symbol theta, okay, which is some fixed value. Like if we wanted to, we could open up the pouch, dump everything out, and we would get a fixed value for theta. We just don't know what that is, okay? Then whatever that theta is, the likelihood of our data, where I got 4 red marbles, 6 non-red marbles, would be theta to the 4, 1 minus theta to the 6, okay? And we can do maximum likelihood estimation. Maximum likelihood estimation, if we drew 4 red marbles out of 10 marbles, our maximum likelihood estimate would be 0.4. That's, I think, intuitive, okay? But then I want to ask, how confident are you in that estimate? It's based on just 10 observations, okay? So your answer is probably not super confident, okay? You'd feel a little bit better if we had observed like 100 observations or 1,000 observations, okay? And if you got that, then you'd say like, okay, whatever number I have, I'm pretty sure the true value's got to be kind of close to that. But if we've only seen 10 things and 4 of them are red, and I said, hey, you know what, the actual proportion in here is 0.5, none of you would bat an eye, right? You'd be like, okay, yeah, that sounds about right, okay? But if I said, hey, you know, the actual value was, you know, it's actually 60% red, you'd go, oh, okay, I guess that's also possible, right? And it's only until I say like, oh, you know what, the actual value was like 90% red, you go, oh, that's kind of weird. How did I only get 4 red marbles, okay? Or something like that, right? But getting, you know, if your maximum likelihood estimate is 0.4, and you find out the true value is different by, say, like 10 percentage points or even 20 percentage points. You know, if the true value was like 60% red and you got 40% red in your sample, even that wouldn't be super shocking, okay? But if, say, I drew like 1,000 marbles, after 1,000 marbles you got 400 red marbles, and then I said, oh, you know what, it was actually 50% red, you'd be like, whoa, something weird happened, okay? Even something like if I said, oh, you know, it was 45% red, okay? With 1,000 observations, you know, being off by, say, 5 percentage points feels like a lot, okay? And that's reflected in our likelihood function. So if I plot this, right now I've got 4 red marbles, 6 marbles that weren't red, so my likelihood is theta to the 4, 1 minus theta to the 6. If I plot that, the likelihood function looks like this. And so we can see, you know, maximum likelihood indeed is when theta is equal to 0.4. But when we look at this, we also see, oh yeah, you know what, the likelihood when theta is 0.5, somewhere around here, you still have relatively high likelihood. Theta at 0.6 is still relatively high, and it's only until you get to like theta is 0.8 or 0.9 where that likelihood really drops off. Okay, and similarly, the true value of theta 0.2, it's not super high, but it's also not incredibly low. And it's only until you get down to like theta is 10% or theta is 5% that the likelihood is really low. Okay, so this likelihood function, kind of tells us where we have our maximum likelihood, but it also shows that other values have high likelihoods as well. Okay, so now we do the same kind of thing where I have 1,000 marbles, or not 1,000 marbles. I draw from the bag 1,000 times, and we get 400 red marbles. Okay, and so now my likelihood is theta to the 400, 1 minus theta to the 600, because this is the likelihood of our data after kind of multiplying the product of all of these things. And if I plot this is what the likelihood function looks like. Okay, so the maximum still occurs at 0.4, which makes intuitive sense, 400 red out of 1,000 draws. But we see that there is a sharp kind of point at 0.4, and the likelihood drops off rapidly as theta changes from 0.4 to say 0.42 or 0.43. And by the time you get to say theta is 0.5, the likelihood of your function is practically zero, indicating that if we did indeed observe 400 red marbles after 1,000 draws, it would be really shocking to us to find out that the bag was actually 50% red, because the likelihood of getting my data where only 400 were red is really, really, like, it's practically zero here. Okay, so the probability, if the proportion was really 0.5, how are you going to get 400 red out of 1,000 draws? It's almost impossible for that to happen. Okay, and so really anything outside of this range of, like, I don't know, what is that, 0.37 to 0.43 or something, becomes really unlikely. Okay, so here I just say the pointiness. Okay, but kind of just the idea that when you look at this, the likelihood function, I don't know what the formal term is, but yeah, the graph, it's very pointy at 0.4, indicating that only values that are close to 0.4, like 0.39 or 0.41, have high likelihoods. Values like 0.3 or 0.5 have much lower likelihood. Okay, and so in this case, the variance as far as what theta can be is much smaller. Okay, compared to this likelihood where theta could be 0.3 or 0.4 or 0.2 or 0.6, all over the place, and it's quite possible. Okay, so this is all. We can kind of relate this back to our second derivative. So if you take the log likelihood of our first function, where we only had 10 draws, the log likelihood based on 10 draws is this. And if you take you get 4 log theta, 6 log 1 minus theta. The first derivative is 4 over theta times plus 6 over 1 minus theta, and the second derivative is negative 4 over theta squared plus negative 6 over 1 minus theta quantity squared. Okay, so this is our second derivative of the log likelihood. I can do the same thing when I have 1,000 draws. My likelihood function is theta to the 400, 1 minus theta to the 600, and this the second derivative ends up being negative 400 over theta squared plus negative 600 over 1 minus theta squared. And so we can see that this log likelihood and this log likelihood are almost the same. It's just this one is a factor of 100 higher than this one, right? So it's just I take this, and if I multiply it by 100, then I will get my I guess the second derivative of this one. Okay. If I were to plug in kind of the log likelihood at the point 0.4, okay, so my maximum likelihood, my likelihood is maximized when theta is equal to 0.4. If I plug that in, then the second derivative of the log likelihood here is 41.667, and over here it's 100 times that, negative 4,166.7, okay? And this kind of second derivative measures the curvature of the function. It tells us what we know, that the second derivative on this function is much greater than the second derivative at the other function, indicating that the change in slope is much more rapid for this one, which indicates to a function that's much more pointy. Okay, so if I kind of go back, if you think about what is the slope over here and what's the slope over here, we go from something that's very steep positive slope to very steep negative slope in a very short distance here. Okay, so the change, that slope changes rapidly, so we're going to have a very high second derivative. If we go to this one, how does the slope change from over here to over here? Okay, kind of in that same kind of region, we go from gentle positive slope to gentle negative slope. So how quickly did that slope change? It changed relatively slowly. Okay, and so that corresponds to a much smaller second derivative. Okay, so so we can kind of take that. Oh, here, before I get into that, let me give you your second view quiz answer, which is the letter E. E as in elephant. Okay, so the fact that this likelihood function has much more curvature in the second graph, where we had 1,000 observations, indicates that the data we have provide a lot more information about the location of theta. Okay, and intuitively, that actually also makes sense. If you have 1,000 draws of, from the bag, okay, we basically have 100 times more information about what theta should be than we did after only 10 draws. Okay, so the idea is like we're trying to figure out what theta is based on the draws. How much information do I have? With only 10 draws, I only have a little bit of information. With 1,000 draws, I have 100 times that amount of information. Okay, and so that's that's reflected in kind of the numbers that we're getting here. Okay, and so the relationship between all of this, the curvature of the likelihood function, the information that we have, this is all tied together in this concept of the Fisher information. Okay, so the Fisher information is a way for us to kind of measure the information a random variable can provide about some unknown parameter. Now, the technical, I guess the formal definition of the Fisher information is that it is the variance of the score, and then the score is the derivative or the gradient of the log likelihood. And so I guess you're asking about, what is the variance of that, the gradient of the log likelihood? That's I guess one definition of the Fisher information. One kind of to relate it back to what I've been trying to show you, all of this stuff, okay? The Fisher information is also equal, all right? So if you have this, if the log likelihood function is twice differentiable with respect to theta, all right? So that's going to be a lot of functions, but not every single one. The ones I've shown you, it's true, okay? So if the log likelihood is twice differentiable with respect to your unknown parameter, then the Fisher information is equal to the negative of the expected value of the second derivative of the log likelihood. Okay, so we've been talking about the second derivative of the log likelihood, and then the Fisher information is basically the expected value of that second derivative, but then you make it negative, okay? So we'll say, we have some kind of function f, okay, given some parameter theta, and so that is to say the Fisher information, which we indicate with this, I don't know, fancy I, is you can take the second derivative with respect to theta of the log likelihood, okay? And then once you have whatever this is, then you take the expected value or the negative expected value of that, okay? So we can also write it like this, negative expected value of f of x of theta of this. All right, the expected value is taken with respect to the random variable, which is defined by this function here. Okay. Do you guys cover Fisher information in your other classes as well? 100B. Okay. All right. Maybe? Yeah. Okay. All right. So, well, this is just that. Okay. So here, if we did like for one Bernoulli observation, okay. So this is just, you know, like we picked one marble out of the pouch, okay. Then our Fisher information would be something like this. So here our likelihood function for one observation is theta to the x, 1 minus theta to the 1 minus x, and I want, and it's the, we're going to take the log likelihood, so we get this, and we're going to get the second derivative of this. Okay, I'm going to split this up into log of theta x, and then plus second derivative of log of 1 minus theta to the 1 minus x. Okay, and just kind of log rules, I get x log theta and 1 minus x log 1 minus theta. The first derivative is going to give me x over theta, and I get negative 1 minus x over 1 minus theta, and then the second derivative gives me negative x over theta squared plus negative 1 minus x over 1 minus theta squared. And if I say, okay, what is the negative expectation of this? Okay, we're going for the expected value of x with respect to x here. So here I'm going to get the expected value of x divided by theta squared, and the expected value of 1 minus x divided by 1 minus theta squared. So theta is a constant with, you know, if we're asking what is the expected value of this thing, I don't have to worry about theta because theta here is a constant. Okay, so I just get the expected value of x divided by theta squared, expected value of 1 minus x over 1 minus theta squared. And if I say, okay, well, what is the expected value of x? If x is a Bernoulli random variable, then the expected value of x is just theta, right? So it can either be 0 or 1. In the long run, it's going to be equal, you know, your expected value is theta. So you get theta over theta squared, and then over here you get 1 minus theta over 1 minus theta squared. And so 1 over theta plus 1 over 1 minus theta, and you can combine that and you get 1 over theta times 1 minus theta. That is your Fisher information after you observe just one observation. Okay. So that's that. Well, okay, so what does this function look like? Where is this maximized and where is it minimized? Yeah. So here, let me just kind of plot it. Sometimes RStudio takes. Okay. Remind me later. It's gonna pop up. I'm not gonna remember. Okay. All right. So let me just do. F is going to be a function of, we'll do theta, and it is 1 divided by, what did I write? Theta times 1 minus theta. Do I have that right? Okay. So we'll do that, and then theta will be a sequence from 0.0001 to 0.9999 by equals 0.0001. Okay. All right. So we'll plot theta and f of theta type equals L. Well, I think let's just I think we're gonna get too much here. Okay. All right, so we get this. So this is kind of our information here. All right. So that's the wait, is that right? Negative expectation of this, yeah. Okay, so that's my my Fisher information here. If you have a whole bunch of observations, okay, we end up, it's additive, and so you'll get n times this. You could also kind of do the math plugging in if you have n observations and whatnot, okay? You'll also end up arriving at the same kind of thing. So if you do like a binomial experiment and you talk about, you know, how many total n trials did you have and how many x successes did you have, you'll end up kind of getting similar kind of same answer there. Okay, so this kind of demonstrates that, you know, the second derivative of the likelihood function told us kind of how confident we can be in our parameter estimates. We want to generalize this to the multivariate setting, okay? And so if we think about the second derivative here giving us information, our Fisher information, this was just for a univariate case. If we do it for the multivariate case, we'll get the Hessian matrix. All right, so kind of doing that, the same idea here. The Fisher information matrix for kind of a multivariate function tells us how much information our data provides about the unknown parameters theta. And if our log likelihood is twice differentiable, okay, then the Fisher information is the negative expected value of the matrix of second derivatives, or negative expected value of the Hessian matrix, okay, of the log likelihood. So basically, same kind of thing. Now I have, this thing is going to be a matrix of things, and our Fisher information is going to look like this. This is each kind of component within our Fisher information matrix. The ith and jth component will be with respect to theta I and theta j. Okay, so so we can look at this and think about this for linear regression. Okay, so for linear regression, our unknown parameters is going to be w. Okay, and the outcome variable is t. All right, so we're assuming the errors are normally distributed. Okay, probability is going to be kind of the normal PDF with the mean W transpose XN, variance sigma squared. Okay, we're going to treat our XN as fixed values, our sigma squared as fixed values. And so the Fisher information is the negative expected value of the Hessian of the log likelihood. The expected value is taken with respect to the outcome variable t, and that t distribution is defined by the probability distribution of this centered around the normal distribution. Okay, so we want to say, hey, what is the expected value of this thing? Okay, this thing, basically I've got the product of all of my normal PDFs, and we want to know what's the Fisher information that, you know, our W provides. So kind of going through this, you know, we take the log likelihood of all of this, and you know, my W vector, like if I have just a slope and an intercept, I'm going to get a 2 by 2. If I have like multiple x terms, I might have 3 W terms, and I'm going to get a 3 by 3 or something like that, right? So our so the first derivative, this will give us kind of our the first derivative of the log likelihood gives me this, kind of jumping through it. I get so this is a length k vector. So if we just have a slope and intercept, I've got basically a length 2 vector, and right now that's going to be 1 over sigma squared x transpose t minus x transpose xw. And I think I've already shown you the steps on how to do this, I think in Monday's lecture. And then if we take the second derivative of this with respect to w, okay, or I guess the Hessian, the gradient, or I don't know, whatever, partial with respect to w, and you say, okay, what is that? Okay, well, this thing goes away. There's no w in here, okay, and basically I just get this, and I'm going to get negative 1 over sigma squared x transpose x. All right, and that's going to be, you know, this is a second derivative of the log likelihood, and so now I want, okay, so that's the Hessian matrix. The Fisher information is the negative expected value of this thing. Okay, so how does, what is the expected value of t with respect to this? Okay, well, t is kind of, for t, x, and we're treating x and sigma as constants, so there's no, like, I'm not going to replace x with anything, and I'm not going to replace sigma with anything. It'll just be this. The negative of this is going to give me 1 over sigma squared x transpose x. Okay, so that's my Fisher information. What does this mean? Okay, well, here I have 1 over sigma squared, okay, indicating that if if there's little noise, okay, then sigma squared is going to be small, and I will have high information. Okay, so if we have that, if sigma is large, okay, sigma squared is large, then you have kind of a lot of scattering, and you're going to have less confidence in the estimates of W. You also have x transpose x, which indicates that the size of x itself plays a role. All right, sorry. Let me give you your last view equals answer A, but I also want to kind of illustrate this. Okay. Let's say you have a few dots here. Okay, and you're trying to get a slope estimate. Right? If you have basically a small range of x values and you're trying to get your slope estimate, you're going to have kind of like high variance here, right? Okay. On the other hand, if you have, I don't know if that's kind of shown here. If you have dots over here and dots over here, so actually, let me just kind of, how much variance do I have? All right, so we're gonna have like small variance in our things. Then I could be very, sorry, that should be a straight line. Okay, I can be a lot more confident in what my slope is, right? I'm not gonna have as much, how much can my slope vary? It's not as much versus like if the x values are all kind of bunched together, okay? And that's reflected in here. Actually, the magnitude of x itself matters because that's also going to play a role in like your intercept and things like that. So, but yeah, if you are trying to estimate the slope over time, right, and you take a measurement today and you take a measurement tomorrow, okay, and you're going to say, okay, well, how much does stuff change over time? You're going to have kind of like a lot of variance in that thing. Versus if you take a measurement today and you take a measurement like a year from now, okay, and you say, well, how much does something change over time? Like if you're trying to like estimate how much does someone's fingernail grow in 1 year, okay, and you take a measurement today and a measurement tomorrow, your estimate's going to be pretty bad, okay? Versus an estimate, like if you take a measurement today and then somehow you were able to wait an entire year without clipping your fingernail or something, then your estimate's going to be a lot better, right? And that's kind of reflected with this x as well. Okay, we will wrap it up here. I gave all 3 view quiz answers, right? Third one is A. All right, so we'll end there. Okay, have a great rest of your day. And we'll see you Friday.